Hello everyone, welcome to another edition of the UK Quantum Fluids Network webinar. And today's speaker is Sergej Moroz from Karlstad University in Sweden. So you can start the presentation, Sergej.
Okay, thank you very much, Dima, for the opportunity to share some kind of thoughts on superfluid vortex crystals, and also our thinking about how they can melt at zero temperature. I will not see the chat, so please let me know if somebody asks anything there. And please, interrupt me at any point with questions. So I will start with introduction of vortices, right? So this is the swirling excitations, which appear already in also in classical fluids, but in quantum fluids and superfluids, they are special because the integral around them of velocity is quantized in units of h bar, so they manifest quantum mechanics on microscopic scales. And I will be talking about essentially two-dimensional vortex crystals, so you should think about thin films of superfluids, and their vortices are just points, right, where this kind of singularity in the phase is. And so what I would like to point out is that what is interesting already about a single vortex is that it follows this non-Newtonian dynamics. Instead of having kinetic energy, so here x and y denotes x and y position of a vortex, and here I'm writing a Lagrangian for a vortex, and you see the first time derivatives only, not second time derivatives. So the leading term, the leading kinetic term, has first time derivatives, and here this ns is a superfluid density. So this has a long this has important consequences. In particular, if we take a vortex system and quantize it, and compute the commutation relation, or for the Poisson break it and then compute the commutation relation, we see that we cannot simultaneously determine x and y with arbitrary precision. So intrinsically, vortex is a fuzzy object, and fuzziness of this vortex is fixed by the inverse of superfluid density. So this is quite interesting on its own, and we will talk about it more later. If you look into this Lagrangian function, you would notice that it looks like a effective Lorentz force acting on a vortex, where the role of magnetic field is played by the superfluid density. And I will also come back to this fact later. So in order to get a lot of vortices, if we have charged superconductors, we need to turn on external magnetic field in type 2 superconductors, as Abrikosov found already back in 1957. There will be a crystal formed of vortices, and in neutral superfluids, the role of magnetic field is played by external rotation. And so we have these vortex crystals both in helium superfluids, but also in cold atoms, as shown here. And if you want to describe vortex crystal in superfluid, you can treat it in two particular limits. One of them is like thin vortices, when the coherence length is the vortex density is times coherence length squared is much smaller than 1. And that's the so-called Tkachenko regime, where superfluid can be viewed as an incompressible fluid, and vortices are just thin points in this the defects. But then there is another regime, which is when the coherence length becomes large, and it kind of starts. So vortices essentially start to overlap, and we get these fat vortices. And analytically, the treatment of this regime can be done by projecting on lowest Landau level. So you look for the solution of the Gross-Pitayevsky equation in the lowest Landau level submanifold. And this goes back to Abrikosov. And this is essentially will be the main interest for me, this lowest Landau level vortex crystals. So in particular, I'm interested in how these vortex crystals can melt in 2 dimensions. And this question, due to melting due to thermal fluctuations, has been studied for a long time, going back to 80s. And I think the consensus is that this kind of vortex crystals go from a crystal to a fluid through a intermediate nematic or hexatic fluid phase, and the transitions are believed to be Kosterlitz-Thouless transitions, where different types of topological defects, the dislocations and disclinations, proliferate. So what I'm interested in is what happens at 0 temperature in the system, because it's easy to argue that vortex crystals should melt due to quantum fluctuations even at 0 temperature if you crank up rotation rate or the effective magnetic field. And the intuition here is that, as I was already describing, these vortices are intrinsically fuzzy, so they have kind of an area of uncertainty where they are, which is fixed by the inverse superfluid density. Sorry, I sometimes change the subscript. So NB means here density of bosons, so it's a superfluid density. And as soon as this kind of fuzziness becomes comparable to the intervortex distance, then we can imagine that the vortex should melt, right? Because we cannot say exactly like the fluctuations of the position becomes comparable to intervortex distance. And this can be nicely kind of characterized by the notion of the fill-in factor, so which is a ratio of density of bosons to the density of vortices. If this fill-in factor is very large, we end the vortex crystal phase. But then as this fill-in factor goes to order of 1, we expect some kind of melting to a strongly correlated phase. And we know some of these phases at some particular fillings, such as nu equals 1/2 or nu equals to 1. But it would be nice to find out what happens around this order unity filling. There is some exact diagonalization studies which suggest that it's something like 7 or 8. So I would want to understand what are possible ways how this vortex crystal can melt. So this is the motivation. So are there any questions? Are there any questions so far? If you have any questions, feel free to ask at any point, as I said.
Yeah, I think just unmute yourself and ask a question if you have any. Yeah.
Yes. Okay, so it looks that everything is fine. So let me get into the outline of the talk. It's quite ambitious, but we will get as much as we will get. So I will talk about effective field theory description of these vortex crystals, meaning which encodes collective excitations at lowest possible energies and momenta. And I will argue that the proper theory for this is what is called Lifshitz effective theory. So I will try to show you how to derive it, and then I will try to apply it and make some predictions of possible transition. And then I will talk about what is called dual description of this Lifshitz effective theory, which incorporates naturally topological defects of a solid, which are disclinations and dislocations. So it turns out that it's very natural to introduce this dual tensor gauge theory, and we'll talk about it as well. And then in the second part of the talk, if I will have enough time, I will tell you about nonlinear effects. So this part will be about like linear theories, so both Lifshitz and this dual gauge theory, but I will try to argue that actually, due to symmetries, we can fix certain nonlinearities, and these nonlinearities will allow us to make a prediction about how the collective mode, which is a Tkachenko wave, how it decays at low momenta. And in the end, if I have time, I will also mention that if we try to incorporate the nonlinear effect into this dual gauge theory, then we get some kind of effective emergent gravity, dynamical gravity. And I will share some thoughts about it. It's kind of work in progress, but I will tell you a bit. Okay, so let me first talk about how to think about effective theory of this vortex crystal. So we want to describe the physics that, we want to have a coarse-grained description in terms of thinking about a vortex crystal as some kind of superfluid elastic medium, right? Somehow, where superfluidity and elasticity interplay with each other. And so we need to incorporate vortices into superfluidity, and these are defects of the superfluid phase, but there is a kind of a nice description of that, which we already kind of touched upon. So vortices actually behave in a superfluid like charges, right? Somehow, for example, they feel this Lorentz force. They feel like they like, and so it turns out that this effective Lorentz force it's not a coincidence. It's a part of like a alternative description of a vortex crystal, which is known as boson-vortex duality, which is a mathematical mapping between the theory of superfluidity, the XY model with topological defects, which alternatively can be described as a gauge theory in 2+1 dimensions, where gauge field describes superfluidity. So superfluid density maps to the magnetic field, superfluid current to electric field, the phonon or the Goldstone boson maps to a photon, and then the vortices are like charged matter, which couples minimally to this gauge field. So I will use this language first to get to the, and so in this picture we have this medium, right? Somehow where we have these vortices, and they will be described by displacements, right? Coarse-grained displacements from equilibrium position to capture elasticity. And then superfluidity, as I was saying, is captured by this dual gauge field, which lives in 2+1 dimensions and propagate, vortices exchange this kind of photons with each other. And we can view it as some kind of, in this language, it's some kind of Wigner crystal of charges, right, somehow, which lives in a background magnetic field. And this background magnetic field is just the density of the background density of the superfluid. And so now I argue that, okay, so first, what are the collective modes of this theory? This theory will depend on UI, which are the coarse-grained displacement, and on this A mu, which is a gauge field describing the superfluidity. And naively, one would thought that like there is a independent, right, somehow phonons, because it's a solid, and also Bogolubov phonons or Goldstone modes related to superfluidity. But it turns out that actually these two sectors interplay with each other and hybridize in such a way that at low energies, there is just one collective mode called Tkachenko wave. And this, at very low momenta, it disperses quadratically with momentum, somehow. So the energy is k squared. So it goes as parabolically. And the polarization looks like elliptically. So, and as we go closer and closer to low momentum, the polarization becomes more and more look like, you know, transverse. So this ellipse kind of squeezes. And here my aim is to actually zoom in at the lowest possible energies. So forget about this, what is called cone mode, which happens at the twice rotation frequency, you know, and just zoom in at the very lowest frequencies and try to describe everything in terms of this like this mode only. And this will lead to this Lifshitz theory, which I will try to describe on this slide. So as I told you, like effective theory, which I was kind of alluding to here, is an interplay between coarse grained displacements and the gauge field, U1 gauge field. And here I write you the leading order Lagrangian for that. So we have these vortices and they have this Berry term or Magnus term, you know, which I already told you about, which gives rise to this effective Lorentz force, and this first in time derivative dynamics. And then there is elasticity, right? Somehow it's an elastic medium. So this kind of strain tensor gives rise to compression and shear contributions. And then it should couple to the, you know, dual electromagnetism, which describes superfluidity, and one would expect to see E squared minus B squared, electric squared minus B squared. So it turns out that in the lowest Landau level approximation, where you make, you know, the gap between Landau levels very large compared to interaction strength, you can drop the electric term squared. So it is just disappears. It's only dual magnetic term, which appears here, which effectively describes density-density interaction between original bosons. So now these two sectors, the elastic and the superfluid, they talk to each other, they intertwine, and they intertwine through this kind of dipole term. So whenever you move your vortex away from like equilibrium, you get a dipole contribution in E times U, where E is a dual electric field, which is related to superfluid current. So this is my starting point. But now I will argue that this is too complicated actually. And to see that, you can start analyzing this effective theory. You start to solve equations of motion, and one of the equation of motion is just, you know, the Gauss law. So the variation with respect to A naught, the scalar potential. And this originates from this term, and you can see that immediately that from the Gauss law, you get that the divergence of U is equal to 0. So this means that the vortex crystal at very low, you know, energies behaves in an incompressible medium. So you cannot kind of compress it. And for this reason, the Ux and Uy are not independent functions actually, right? Because they satisfy this constraint. And in fact, you can solve this constraint by just representing U as a skew derivative of some scalar function phi, right? If you would substitute it into here, you would see that it automatically satisfied. So this means that actual like field which describes your vortex crystal at very low frequencies, like energies, is this field phi. Now, if you substitute it into here and integrate out superfluid fluctuations, you end up with this theory. And this is something which is called Lifshitz theory. So phi here, which by the way describes regular part of a superfluid phase. So you have phi dot square term. And then notice that here, instead of the first derivative of phi, you have Laplace of phi squared. So this is why it's called Lifshitz. So the scaling of the temporal derivative and the spatial derivative is different in this theory. And here the constants. So lambda is a short-range interacting kind of constant between density boson interaction. B naught is an effective magnetic field fixed by rotation, and C2 is a shear modulus. So C1, the compression modulus doesn't appear in this regime. Now, if you compute the collective mode, you would find that omega squared goes as q to the fourth, and this is what I already told you about, that at very low momenta, it scales quadratically. Any questions about the Lifshitz model? Okay, so let me move on. So what can we do with this? One thing is that, it's a quadratic theory, so you can start thinking about what kind of operators or kind of you can write and evaluate its correlation functions. And so, this is a compact field, this phi should identify 0 and 2 pi. So if I rewrite it, if I normalize it a little bit differently, this Lifshitz model, and put everything into this eta, then I can write these two types of what is called vertex operators. One of them is just the exponential of phi with some integer n. Given that this is quadratic theory, you can compute the equal time correlation functions of this which I call electric vertex operators, and you can see that they decay as a power law as I spread the insertion of these operators, and the power is fixed by this integer n, but also by this eta, which is a coefficient which stands here, I can fix this coefficient in terms of my theory here. I know, for example, how C2 is in the lowest fundamental level approximation. There is a microscopic formula for the elastic modulus, so on. So I can actually evaluate this eta. But before I do that, there is another type of operator which you can think about, and this would be like creating a vortex of this phi, right? So this phi is a collective description of a vortex crystal. So we have a lot of vortices already there, but this phi describes a regular part of on top of that. And but I can think about creating a vortex of this phi, and this is done by taking a canonical momentum, canonical momentum to phi, and shifting the field then with a profile, which is just a vortex profile around some point x, right? So this is kind of places a vortex, and it's also possible to compute correlation function of these operators, and also it decays algebraically as we spread the distance, and it's also fixed by this eta in a bit different way, but everything is controlled by this eta. So now you might wonder what actually this means physically. So we need to have some interpretation of this for these fields. And so the first field, the electric one, you can see that we are just adding e to I and phi is a field, is a phase field of the boson. So essentially we are putting microscopic bosons in with these electric operators. And here is the algebraic decay of this correlator is something which is quite well known in the vortex crystal literature, is that despite being at 0 temperature and despite being in 2 dimensions now, we have no long-range order in U1, in the particle number. So the elasticity fluctuations make destabilize long-range order, and we have only quasi-long-range order in vortex crystals in 2+1 dimensions at 0 temperature. But let's think about the magnetic operator, right? I told you that it creates a vortex of phi, and interpretation of that is to create a vacancy or interstitial in a vortex crystal. So on top of a background, which is fixed by rotation frequency, we can think about creating extra vortex or taking away a vortex, right? And this appears to cost energy, right? Because due to elasticity, it costs a certain amount of energy, which I show here by this dashed line. But you can think about the following scenario, which goes back to Andreev and Lifshitz when they thought about supersolidity in usual crystals, while adding isolated interstitial vacancy costs energy. This defect is able to hop now on a dual lattice. Let's say if I put interstitial extra vortex, it can hop, and by hopping it will create instead of a flat band, you would get a dispersion, and some part of this dispersion will be below that energy, elastic energy, and we can imagine that under some conditions it can touch zero, right? And then it would be advantageous for system to condense this kind of excitations because they cost nothing. And this is exactly the scenario which I'm thinking about here. So I want to understand if this kind of condensation of vacancies and interstitials, provided it happens in microscopic model, if it destabilizes this vortex crystal, and if we get away from this Tkachenko wave. For this correlation length, which I kind of, or this exponent is very important. So this exponent is, you have to compare it with a critical exponent, which in the Lifshitz theory in 2 + 1 dimension would be delta equals to 4, because you get 2 from time and 2 from space. We are in 2 spatial dimensions, and so if this delta of this magnetic, imagine m equal to 1, so I'm just creating a single interstitial, and I'm kind of now need to evaluate this, and I told you this eta can be evaluated, and this delta is given by, turns out to be given by this formula. It's some number times the fill-in fraction, which fill-in fraction is just the density of bosons to the density of vortices, which is fixed by effective magnetic field. And so now we need to compare this with delta equals to 4, and for fillings which give us delta which is smaller than 4, we expect that in the renormalization group sense, the effective theory should flow away from the Lifshitz theory, and you should get into a different phase. And so it turns out that this nu then is equal something to 8. And so the conclusion from this is that it appears that if this proliferation of vacancies in some microscopic theory happens below, fill-in 8, then we should expect that the vortex crystal will be unstable, and it will flow to something which we can call like vortex supersolid, where vacancies of vortex crystal proliferated. But if it happens above the filling of 8.2, then it should be irrelevant, and then it should not change the low energy physics. So this is how we can use the Lifshitz theory to make some kind of some kind of predictions about the condensation of vacancies and interstitials. So now I will move to the next topic. So are there any questions about this discussion? Okay, it appears not. You can still hear me okay, right? Just to be sure.
Yes, sure, we can hear you.
Okay, good. So then let me move on now to this what is called fracton-elasticity duality. The idea here, which goes actually back to 80s, but it has been revived recently with advent of these fractons, is that we want to think about, when we think about how crystals melt, we want to think about their topological defects and their proliferations. And the topological defects in a crystal are peculiar, so they're called disclinations and dislocations. And dislocations can be viewed as dipole of disclinations, and they are peculiar because they have certain mobility constraints. So we know that in crystals, these disclinations are very energetically heavy and they essentially cannot move, while dislocations can move, but only in particular direction. So they can move along what is called Berger's vector, but they cannot climb, so they cannot go perpendicular to that. And this kind of mobility constraints, or what is called fractons, can be incorporated through a duality. So once again, the idea here is similar to what I was telling you before. These are topological defects of translation symmetry breaking of a crystal. And instead of thinking about like regular and singular parts and so on, we want to actually view these things as some kind of charges and dipoles of charges, which couple to some kind of gauge field. And here, because we are thinking now about translation symmetry breaking, and there are like two directions, X and Y of translations, the gauge field happens to be a tensor, not a vector gauge field, but a tensor gauge field. It has two indices. And the nice thing about it is that if you build up this theory, as I will show you later, you can see how these defects couple to the gauge fields. So the pure gauge theory will encode like phonons, somehow, and the coupling to the topological defects is very natural through minimal coupling in the gauge theory. And now if you want to proliferate these defects, disclinations and dislocations, you can do what is called, you can condense your matter in this gauge theory or do what is called Higgs condensation of defects. And that's what I will try to describe to you here. But first, let me kind of briefly show you how to go from the Lifshitz theory of a vortex crystal to a theory of tensor theory of dual tensor theory. So here I write my starting point, which is the Lifshitz theory, right? Phi dot squared, and here is second derivative of phi squared. I write the second derivative in this particular way because actually this has a root from shear elasticity. U is a skew derivative of phi, and then if I want to have a shear contribution, it actually is important in order to couple properly to defects to write it carefully in this way. And so my claim is that I can dualize it by following some standard steps, in particular do some kind of Hubbard-Stratonovich transformation and change the degrees of freedom from this phi to something which looks like a gauge theory. So it's not obvious right now, but let me just try to highlight what this gauge theory, how it looks like. So we have electric field, which has two indices now, and this electric field is a traceless symmetric tensor, and what it encodes physically is a stress tensor of the vortex crystal. So, and then we have a magnetic field, which has no indices, as you can see, and this is similar to what in the vortex boson duality was. It encodes superfluid density fluctuations. So this is essentially the density fluctuations on top of a background. And then the claim is that this theory encodes the Tkachenko wave and quadratic dispersion, but now the minimal coupling to some matter, which is given by rho, and a current which has two indices now, I and J, is exactly coupling to topological defects of the vortex crystal, which is disclinations and dislocation current. So this is kind of, I don't show the derivation, but I would like to first talk about this theory. So imagine I did this. So first of all, you might wonder, is it really a gauge theory, right, somehow? And so you can probably guess that it is probably because not only E and B appears, but also there are these gauge fields. But one reason why we need gauge fields is also because it turns out that this E and B in this kind of in this formalism are not completely independent. They satisfy a constraint, which says that the time derivative of the magnetic field, of this dual magnetic field, is a second derivative of this electric field with two indices. And you might wonder what it means, but it turns out that it has a simple explanation. So here you have a dTn, essentially, the superfluid density. And so here you have second derivative of a stress tensor. And it turns out that in the lowest Landau level approximation, which I'm interested in, the first derivative of a stress tensor is related to a superfluid current. And so what I kind of secretly wrote here is a conservation, particle number conservation, when I restrict to the lowest Landau level. But in order to resolve this constraint, right, so B and E are not independent fields, you can see that you can write B and E in terms of gauge fields. So if you write B as some kind of second derivative of Aij, and E as a dt Aij and second derivative of A naught, and substitute it into here, it will be automatically conserved. This means that actually it is a gauge theory, because we need gauge potentials. With the help of gauge potentials, we can resolve this constraint. And to see that it's a gauge theory, you can also convince yourself that these two building blocks, the B and the Eij, are invariant under gauge transformations. And these gauge transformations are peculiar. So for A naught is just a usual gauge transformation with a dt beta, where this is a gauge parameter, but Aij has two indices, so we need to do second derivative of beta. And under these transformations, you have, both B and Eij, which are physical, right? Somehow this is superfluid density, and this is a stress tensor, so they remain the same. Okay, so we have this peculiar gauge theory. And so now you might wonder what we can get from that. And so you see that if you look into this Lagrangian, everything is gauge invariant except for these two terms. And so if you now do gauge transformation to this part, and you compute in the action, you can see that you will get from the gauge invariance of this part, you will get of the action, you would get a conservation law of the defect, density and current. And this conservation law looks like this. So dt rho, is fixed by the second derivative of Jij of the current. And there is this trace subtraction. So if you think about what kind of matter, satisfies this conservation law, you can convince yourself that this is quite peculiar, because this obviously says that the charge is conserved, right? If you just integrate it over whole space, this will fall away, and the charge is a constant. But it's not only the charge is conserved, but also a dipole. So this kind of combination is also conserved. So the two components of the dipole is a conserved charge, right, somehow. And moreover, because I'm subtracting this trace, there is also some kind of trace part of the quadrupole. So rho times x squared is also automatically conserved by this equation. So you see that the motion of the charge is actually quite constrained here. Because, for example, if you have a unit of you have a charge rho, you cannot just move it the way you want, because this would violate the conservation of the dipole. And this is not allowed. by this conservation law. So charges in isolation cannot move, and the dipoles turned out, because of this extra conservation law, they have to follow this glide constraint, and this essentially reproduces the things how disclinations, dislocations, how they behave in solids. So you see here, it follows essentially from this gauge invariance. From this theory, it was also quite easy to compute interactions between different defects. So for example, if you take two dislocations and measure the potential between them, there is a potential mediated by this gauge field. It's like solving now, Coulomb problem, but in this exotic gauge theory, you would find some kind of logarithmic potential between dislocations with some dependence on the direction of the Burgers vectors. So these vacancies and interstitials are a little bit tricky in this formalism. So, but let's concentrate on dislocation and disclinations now. Okay, so other questions about what is the idea and how we got this theory roughly? Looks like not. Okay, so what can we do with this theory except for these interactions? So I would like to argue now that I can think about so what we'd have in a superconductor. If we have a superconductor and we add matter to it, right, somehow, we can condense or do Higgs transition and gap out the photon and get collective modes in the superconductor. So here I can try to do something similar. And the interpretation is that I would like to condense disclinations, right? Disclinations are my basic charge. And I would want to couple now this theory. By the way, of course, we checked that the collective mode of this theory is just this Tkachenko wave, which I talked about before. There is only one physical mode here because it's a traceless gauge field, and it disperses quadratically. So now I want to kind of condense essentially these disclinations and end up with something like a vortex fluid. So this is kind of a tricky question because it can happen in steps, right? Maybe I first condense dislocations, then I condense disclinations, and so on. So here I would like to consider as the most straightforward scenario, at least naively, and condense everything at once. Basically, by coupling this gauge theory to a charged matter. And so I will consider now a scalar field psi, which describes disclination. And, it's a complex field, so it has a phase and the amplitude. And under the gauge transformations, which I wrote here, right, I would assume that this charged matter transforms in a usual way. But here the problem is that, if I would try to, right now I need to couple this to my gauge fields, but my gauge fields have two indices. So the usual coupling, the IDI psi to some kind of, AI psi does not work. And so here, in order to get some covariant object which transforms nicely under gauge transformations, turns out I need a quadratic term. So the covariant derivative is quite weird. It comes with a square. You cannot write a term with just single field. You need a quadratic term, and then this would be the version of the covariant derivative, which couples minimally to the gauge field. And this is quite tricky, right? Because now if I would write the simplest Lagrangian, I would have like psi dt psi, and then I can write this potential, Higgs potential, which depending on this V parameter can have either Mexican hat form, and condense, or just like, you know, essentially form with single minimum. But this term is actually kind of tricky here, right? Because if I do, you know, I need a square of covariant derivative, but in the covariant derivative itself, we have psi appearing quadratically. So this is already quartic term. So you see that even this, what would be usually the kinetic term of, you know, which would be responsible for the superflow here is already quartic. So, but if I just look into this Lagrangian and just think about kind of mean field, then I can imagine that there is a continuous transition when I go with V2 from positive to negative values. This, of course, can potentially be destabilized by quantum fluctuations, and these nonlinearities which appear here might play an important role. But I can imagine that this is, let's think about mean field. Let's imagine that I just go to the essentially negative mass, to the regime where I have a you know, Mexican head potential, and there my psi get a vacuum expectation value, and this becomes frozen essentially, and the most important degree of freedom is the phase. I can think now about what happens after this Higgs transition happened. And if I analyze now this theory in this, you know, in this regime where this psi is frozen, I will see that to my gauge theory, which was written here, now I couple a theory of the phase of chi, which looks like that. This is essentially a Lifshitz theory again, which describe the phase of disclination coupled to the gauge field. So I'm doing essentially analysis now of what we would do in a usual superconductor, but not with a usual gauge field, U1 gauge field, but with this more exotic symmetric tensor gauge field. And similar to superconductivity, what happens is that your goldstone mode becomes gapped, and in addition, you get an extra mode, which has the same gap. In superconductivity, it would be like getting longitudinal and transverse mode. So here, out of the what used to be Tkachenko wave, I get a gapped mode. But then in addition, I have another mode, which has the same gap. And this is kind of related. In a superconductor, this would be a transverse mode, which is related to like decay of the, right, to the Meissner effect, essentially. And so from here, we can also extract the dual Meissner effect. So the dual Meissner effect tells us that the dual magnetic field, so which was, for example, here, right, which is related to the density of superfluidity in this phase, in this Higgs phase, it decays exponentially into the bulk. So the interpretation, by the way, of this phase is quite simple. So originally I had a soft mode in this quadratically dispersing photon, but now I gapped it out, so I do not have any symmetry breaking of translation. So I kind of ended up in some kind of vortex fluid. And in this vortex fluid, the prediction would be that there is a exponential decay of density, you know, density fluctuations if you are close to some kind of boundary. So this is what we can do with this dual theory. We can contemplate about different ways how we proliferate disclinations and dislocations. Okay, so let me see. So this is what I wanted to tell you about what was a linear part of the story. So maybe now it's a good time to ask for questions. Are there any questions about Lifshitz theory or this fracton-elasticity duality? I don't hear anything. So Dima, how much time do I have? Because I need to manage my time, I think. So
It's about 5 minutes, I think.
5 more minutes. Okay, so let me be then brief on that. It's actually quite delicate. Okay, let me try to tell you the punchline maybe without telling you so much the details. But so what is kind of so far I was talking about is always some kind of quadratic theories, be it in the Lifshitz language or in terms of this scalar field or the this dual gauge field, which is equivalent. But now these theories have one important shortcoming, and this shortcoming I will describe here. So in a vortex crystal, we have two types of symmetries, which are both spontaneously broken. One is a like particle number symmetry, and another is translations because it's a crystal. And so in this Lifshitz theory, like you can see how these symmetries act. So phi is just a phase of condensate. So under U1 it just shifts by constant. But you can also notice that because there is this Laplace here, if we shift by a linear function of coordinates, it is also invariant. The action is still invariant. And this is related to translations because U is a derivative of phi. So under this transformation, U just shifts by a constant. And that's what translations would do. But the problem is that in a vortex crystal, if we take a boson and move it on a closed circle, because there is an effective magnetic field from this rotation, we should accumulate a Berry phase. And this Berry phase should be fixed by the magnetic field threading through this loop. But right now, and this would mean that the two translations, they should not commute with each other. They should commute to the particle number generator times the magnetic field. But now if I look into this magnetic translations and do it in the x direction and in the y direction, they're perfectly commuting. So this symmetry is not encoded in this theory. This is a big shortcoming of that, but it's also an opportunity for us because it turns out that we can have a more sophisticated or treatment of the problem where we can incorporate nonlinear terms, so cubic and higher in phi, which would actually respect this symmetry. And there is a method for that, which for the lack of time, I won't go into. It's called non-commutative field theory. But I would want to tell you maybe what we can. So with this method, we can construct this effective theory and fix nonlinearities in this Lifshitz field phi. And in particular, the physical prediction which we can extract from that is that if we just concentrate on the lowest nonlinearities, which are cubic in the field phi, then we can start thinking about the decay process of the collective Tkachenko wave through this Belyaev decay, right? So when you have a Tkachenko wave and it splits into two, and because of presence of these terms, and also because the dispersion is quadratic, and this is kinematically allowed then, and we can extract the decay constant. And by just dimensional analysis, we can actually fix the dependence of on the energy. So the dispersion is the energy of a quantum is E. The gamma, the decay rate, we predict is going as E cube. And this tells us that this mode becomes extremely sharp as we make Q go into 0. So this is what we can extract from this construction. And this is quite interesting because we find a tension with a previous study. So there was a study using microscopic approach in the lowest Landau level approximation by solving Gross-Pitayevsky equation and fluctuations around it by Matvienko and Shlepnikov, who predicted back in 2011 that the decay should actually go as linearly in the energy. So this would suggest that the ratio gamma to E is a constant, and as we go to very low momenta, it's not becoming sharper and sharper. It's just is fixed. So we have a tension, we have a disagreement with them. Our methods are very different, and it would be very interesting actually to resolve it. So so this is what we can extract from this nonlinear extension of the Lifshitz theory. So let me. Are there any questions about this part? I was very brief, but just about this. Anyone wants to ask anything? Okay, so let me be very quick with this, because I think this is something which is just in progress. I will just tell you the main idea. So since we can extract nonlinear terms in this Lifshitz formalism, one should also expect that in this dual description, there should be some also kind of nonlinear realization of symmetries and so on. And so we came up with kind of an idea that these gauge fields, which I was calling A, J, K, can be actually uplifted to some metric, and this metric satisfies some nonlinear transformation laws. And out of this metric, one can construct an emergent gravity theory, where, dynamical gravity theory, which describes this Tkachenko wave. And if we linearize this theory, we get, the Tkachenko dispersion and so on. But we are interested in this, once again, nonlinear effects. In particular, we want to see that also in this gravitational description, we can also get this decay rate, and in that language it would be the decay of emergent gravitons which split into each other, so from 1 to 2. Okay, so if somebody is interested, I'm happy to tell you more about the construction of the gravity theory, but let me actually finish here with an outlook. So today I told you about like our ideas of vortex crystal, how to describe them at very low energies, and how one can think about melting. And there are different kind of scenarios what can happen. Either vacancies and interstitial can proliferate, and you can get some kind of vortex supersolid, or one can concentrate on disclinations and dislocations and proliferate them and go to some kind of vortex fluid. And so there are a number of questions which kind of I'm interested in. So for example, when we talk about this vacancy proliferation, it would be nice to understand it better with renormalization group, to understand where it actually flows, and also microscopically, really to figure out, is it possible to get this Lifshitz, Andreev and Lifshitz kind of mechanism of vortex supersolid. As I told you, this disclination Higgs transition, which I was talking about, like here, has this like dangerous nonlinearity in the kinetic term, or would-be kinetic term. So this is also like one needs to study it properly, with including fluctuations. This is also something, an open question. And finally, in this gravity theory, which we are trying to develop, once again, it's nonlinear theory. So the gravitons in linear approximation just give you Tkachenko mode. But if you include leading nonlinear effects, they should lead to the decay, and we want to compare the decay with this prediction and also with this prediction. So thank you very much for your attention.
Yeah, thanks a lot, Sergej. So we have time for a few questions. I'll ask a question then about, so what would be a most likely experimental system where you can observe these effects like
Right.
vortex superfluid, supersolid.
Right. I think it's kind of important to rotate quickly. So my guess is that but I'm not an expert. So you want to be in this regime essentially. You want that your vortices are fat, somehow. You want to go to lowest Landau level approximation, meaning that you need to rotate really pretty quickly, like right somehow. I think that recently there were like in cold atoms, they claim even earlier than that actually, right? Somehow there is for example, a paper from Boulder in I think early 2000s where they say that they observed the Tkachenko wave and so on. So I think that the important thing is to go into lowest Landau level. So I'm not sure if for example in helium it's possible to go into the regime of such a quick rotation where the interaction energy scale is much smaller than the rotation, the cyclotron frequency. So probably in cold atoms it's more realistic, but I do not know. Maybe in helium experiments, if you really rotate quickly, it's also possible. The important thing is to have a lot of vortices, of course, like a big crystal. So in a small crystal, you would have a very it's not a crystal. There are these finite size effects. So if you would have a system like that, for example, and rotate even more, then I can imagine that this kind of, so the feeling, right? Once again, the thumb kind of rule of thumb is that the feeling, which is a ratio of number of bosons to the number of vortices, should start somehow approaching order unity. Maybe 10 is enough. I do not know, but I guess this is the way how to be able to guess in which system it's possible to see. We know that at that order something will happen. And
I see, yeah. Probably quite difficult in helium then. So David has another question.
Yeah, can I just make a comment? I remember some experiments in BEC where they rotate very fast the condensate, and then I think that they observed the formation of what they call the giant vortex in the middle. So I mean they go from a sort of crystalline structure to a unique vortex. I was just wondering if this has anything to do with what you've said, or if this is something completely different.
Yeah, I think that what happens there is it's a question of the trap also, right? Somehow. So if you have an ideal harmonic trap, then the system of rotating superfluid and this like particle in magnetic field is completely equivalent. In a sense, when you rotate more and more, the trap kind of flattens, somehow. And in the limit, when these frequencies are the same, rotation and trapping, you kind of have like this infinite system. As far as I remember, in order to get this giant vortex, you need some kind of quartic contribution to the trap or something like that. So, and then energetically, it will turn out to have good to have this giant vortex. So here I'm in the regime where this trap is really quadratic everywhere, and I'm just really getting very close to that the rotation frequency is the same as the trapping frequency. The quicker I rotate, the closer I go I go towards left. And the only technical question is it possible to get to this regime of order unity feeling? If one would get there, then one will start to see some instabilities. But I think this giant vortex is more related that the trap was not exactly quadratic, and they tune it in such a way that this giant vortex ground state was preferable. Yeah. Okay, thanks.
Right, yeah, thanks. So maybe someone still has a question.
Yeah, don't hesitate to, if you have something question offline, I'm happy to answer. So I'm interested in this questions, or in this kind of questions long term. So if people have some ideas, I would be happy to discuss it.
Can I ask a question?
Yes, sure. So,
Yes, there's Haider here from University of East Anglia. So I'm just curious. I mean, I don't know too much about sort of this particular problem, but I'm just curious. There's been some work on looking at edge effects, vortex lattices, and various types of excitations that can arise on edges. And I'm just wondering, I mean, you didn't really discuss too much about edge effects because, I mean, typically in realistic systems, you'll always have a finite size lattice.
Right.
And when you have these higher order derivatives that you're dealing with and all these peculiar features, I mean,
right.
Are these important, these edge effects, to all of this?
Right, right. Yeah, so we studied actually these edge modes in vortex crystals, and I will give you a quick summary of that. So in solids, there is something which are called edge waves, because we are dealing with a solid here, right? And in solids, there is something which is called edge waves, Rayleigh edge waves, actually, somehow, which are excitations, elastic excitations, which are localized near edges. And we did an analysis of that. We were looking for these Rayleigh waves. And in a vortex crystal, we did not find it. So for the particular reason how this vortex crystal is designed, not designed, but how this interplay between superfluidity and elasticity happens, Rayleigh waves are not present in this. So this effective theory is like, does not give you anything. But we studied it microscopically, actually. In the lowest Landau level, we just solved, Gross-Pitayevsky equation, and we looked into the excitation spectrum, and we found edge modes. And these edge modes are like high energy, so they do not start at low energies, which is consistent with the absence of Rayleigh waves, but there are some kind of high energy edge modes, which are chiral, because you break time reversal symmetry by deciding how you rotate. But it is not clear to us what is the physics actually of these edge modes. So we know that they're present like from numerics, but we are not able to develop any like reasonable theory for that. It's not this effective theory, obviously, because it happens at high energies, but there should be some kind of understanding for this. So we wrote a paper, I think in 21 or 22, about this stuff. So if you're interested, you can take a look. But from effective theory, you won't get Rayleigh waves in a vortex crystal. So it's kind of a funny, interplay of elasticity and superfluidity, which.
It's interesting you say that you do observe it in the GP model. So that
in Gross-Pitayevsky, in the lowest Landau level approximation, where you solve for these coefficients, first you find the ground state, and then you study BDG or Bogolubov-Dejean like fluctuations. We did it numerically, and we found chiral modes. But we do not understand the physics of these chiral modes. Yeah.
Thank you.
Okay, well, thanks everyone. Thanks, Sergej, again. And
thank you very much. It was my pleasure.
Thanks. So we'll have next webinar in a couple of weeks' time. It's going to be Giuseppe Baio from University of East Anglia. Thanks, and have a nice rest of the day.